clearly because of the question is not understandable. What approach should I did because of the options also. So can you please discuss the question of how the what approach I should go for, because it's very much not very clear about it. So
So
can you please do the needful, and if you can share the screen also, we will able to I will able to like explain what I want to be explained. So
okay, just a minute. I'll share my
week
screen.
11 assignment 11. Yeah.
Okay.
Okay.
Uh,
It's week 11 assignment 11, question number 7.
Assignment 11, right? I think.
Yeah.
Okay, so I have put my
Question number
answers,
7,
but
ma'am.
whatever. Don't copy them. Uh,
No.
no,
I'm
because they are
just
not corrected
worried
anyways.
about the.
I just put whatever I
Huh,
felt
it's
was
okay.
correct. Yeah.
Yeah, I am worried about the approach, how the options are given, and because if you I hope you have read the question, and according to it, it says that to find the fault in the corner dice. There's a fault in the corner dice, and what is the cause of the faults in the corner dice. So if you do not exactly go to the lab and find out what is the exact investigation of it, and do the corner simulations or Monte Carlo or whatever testing and verification needs to be done. You can't say the exact issue with that. So if you are looking at the options, it can be all or any of the above. If you can say that,
That is correct.
because
Like
it
we
can be
don't have
either
the
for the
exact
litho
process,
or
right?
for resist process.
Yeah, we don't have the
Exactly.
exact
By
process.
seeing the 2D. Exactly. By seeing the 2D diagram, I cannot predict, right? Before doing the lab practices, lab verifications, right? So just I wanted to clear about it.
So, what I think is the way of formulating the question might be a bit wrong. What they might meant to ask is,
Yeah.
like, which all processes can give a,
Uh-huh.
like they are
Exactly.
asking like could have caused. So it like all three are possibilities. Now, which among them that they have to choose? Like they
Uh-huh.
have to study more and understand.
Yeah, either or, like all or either one of them also can be, right?
That
Because
is
I can't predict pinpoint any one, right? Exactly.
that is
And
correct.
in the eighth question, what do they mean by yield? Like the yield of the defect or variability, are they meaning that the variability yield?
For a given defect distribution density within a wafer, one of the following statement is true. Increasing the, let me just unselect. Oh, I can't unselect now.
Hmm.
Okay. For a given defect distribution and density within a wafer, one of the following statements is true. Increasing the die size. Okay. So they're asking, say we know the defect distribution. Uh,
Uh-huh.
so across a wafer, there will be some defects here and there, right? Say one defect here, one defect
All
there,
right.
some yeah. So the
Yeah.
defect distribution and how dense are the defects we know. So that remains
Yes.
constant. Now,
Mm-hmm.
how will changing of the die size or uh, yeah, how will changing the die size change the yield?
Mm.
So this
Yeah.
is my
What
way,
do
right?
what do they mean by yield?
Yield means
Yeah.
oh okay.
Yeah.
So in this case, if you look here, so there are 9 dies
Uh-huh.
in total, out of which 1, 2, 3, 4,
Okay.
5 are working. So the yield is 5.
Yes.
5
Mm-hmm.
5 dies yielded out of 9 is what we say. So the yield is the number of dies that will
Working.
be working. Yeah, working device
Okay. Without defect. Okay,
without
fine.
defect.
Okay.
Exactly.
Okay, fine. Okay. Thanks a lot. Thanks a lot.
Thanks. Okay. Shall we wait for a few more minutes before starting because nobody else has joined?
Yeah, man.
Okay. Okay, so it's 5 minutes past 6 already, so I think we can just start now.
Sure, ma'am.
Yeah, okay. So, yeah. So this is week 11, and so in week 11 we will be discussing about CMP and design for manufacturability. So, yeah. So the first problem is arrange the following CMP process steps in the order in which they occur. So whenever we are doing a chemical mechanical polishing, uh,
Yeah.
we basically have a yes, yeah. We
Smoothing first,
okay, smoothing,
then local, then global.
correct. Smoothing followed by local flatness,
Local, yeah.
then global. So my if my original resist profile is something like this, say, not resist, original
Mm-hmm.
profile is something like this.
Topo.
Topology, yeah.
Yeah.
Say this is some SiO2 and I am trying to flatten this. So what will smoothing do to it? Say it is like this first. Smoothing
Mm-hmm.
will basically just curve it out, right?
Yes.
Yes. And what is local flatness? Akash?
The denser portion will get flattened
Okay.
in the higher side.
Say this was the denser portion. My diagram you can
This was the denser portion.
it will
Yes,
have higher
it will get in
flatness.
the higher side,
Okay.
and then the lower one will be as it is. Yes,
Okay. And then the global
will
flatness will be
fully flattened.
okay.
Will be in the same, yeah, same pitch.
So it is my SiO2. It will be full flat. Okay. Thanks. So yeah, in CMP the polishing pad is regenerated by slurry, polishing head, conditioning head, or platen. So so this is my polishing head here. Did I
Hmm.
mention it somewhere? Okay, I'll just write it.
Yes.
And my wafer will be attached upside down to this polishing head. And this is the pad.
Yeah.
This one is the pad. And then we'll put
Hmm.
slurry, and there will be a pad conditioner. So as we process the CMP, so this pad usually has some microfibers on top of it, microfiber like structures. These are called you remember? These are called asparatites.
Yeah.
Right. So these asparatites, as we start reducing the material on top of this wafer, the that material that is getting removed or etched will get stuck with this asparatites. Also the
Abrasives.
yeah, also the abrasives will come. Uh, so slurry is actually
Yeah.
supplying the abrasives, and these
Hmm.
asparatites are facilitating the movement of abrasives and the reaction with the wafer. So it's
Yeah.
both chemical and mechanical, right? So yeah,
Yeah.
so after some point this aspartate length will start reducing because of this deposited material on top of the pad. So that's why we need to regenerate the pad.
Hmm.
So do you know which of these will help in regenerating the pad?
Conditioning head, because of the diamond tips, it will move up the
Exactly, yeah, it will remove the glaze.
abrasives
Yeah,
and make it rougher. Yeah.
true. Yeah, so the surface will get glazed after a point of time, the pad surface. It will make it
Roughen.
rougher.
Yes.
Yeah. Which of the following affects the thickness of material removed in CMP? Select all that apply. Okay.
Pressure, velocity, slurry composition, and time.
Pressure, velocity, slurry composition, and time.
1, 2, 3, 4.
So why not pattern density?
Pattern density is like it's a prefix thing. So um, thickness of material. Yeah, pattern density is 2, because the more the denser, the like more it will the thickness will be removed. Yes, pattern density to the topography depends on the topography as well.
Yes, yes, yes. You are
So you
right.
can see pattern
So
density. Yeah,
even pattern density will. Okay. So yeah. So just like I
exactly.
said, na in the previous slide. So whenever there is a denser pattern, there
It will
there the material will
remove
be
more.
removed more, less, no?
Yeah. Yes, exactly.
Yeah, there it will be removed less, and other place it will be removed more.
Exactly.
Yeah, so
Yes.
it will be pattern density dependent. Slurry composition, because that will dictate the chemistry. So, and also what all
Chemical. Yes.
abrasives are present in the slurry. And velocity, pressure, and time, that we can say from Preston model.
Preston model.
Yeah, you're right. So I'll just
Preston
write
model.
the
Yeah.
Preston model for others. So the material removal rate, MRR,
MRR.
hmm, is,
Kp into del V by del T. Kp into del V by del T.
so this is the velocity gradient. P is,
Coefficient of Preston model.
okay, coefficient of pressure. It's just pressure, right?
Kp. The total Kp is the coefficient of P in the suffix.
Oh, I thought
Kp
it
is
was
a
Kp
coefficient of
times.
Preston model.
Okay, coefficient
K,
of Preston model.
P is not the pressure here. P is at the suffix.
Okay,
P should be removed from here. Think. Yeah.
it P will be here also, right? Because pressure is also playing a role, right, in material removal.
Uh,
Okay.
yeah, but according to the Preston's formula, P is not there actually. It's just a gradient that is directly proportional, and Kp will be the coefficient for the equality.
Okay, I'll check that. Maybe you're right. This P is not there. Anyways, it will
Yeah,
be directly
exactly.
proportional to pressure, and that coefficient you are saying is in the Preston model. Okay.
Mhm.
Can someone else like verify? I'll just check the net once.
Yeah, P is there because pressure is already dependent, na? So you can write P also in the proportionality. So Kp into P del V by del.
P is also there, right? Yeah, that's what.
Exactly, P is there. Pressure should not be there.
Okay, fine. Okay.
Yeah,
Okay. A batch lithography process is carried out using a stepper tool. Each batch has 10 wafers. So yeah, so in stepper at a go we are putting 10 resist coated wafers, and we are patterning all the 10. A, a particular device is performing out of spec for all dies on wafer 7. Okay, so say this is my wafer 7, it has multiple dies, right? So these multiple dies have multiple different devices. So one particular device is working faultily in all the dies. Okay. However, it's working fine in other wafers of the same batch. Would you classify this as spatial variation or temporal variation? So, so there was a scale of variability slide, right? So a spatial variation means across the wafer whenever we have variation. So that might be due to thickness variation, or resist is not coated uniformly.
I think both. I think both.
Both.
Batch to batch,
This is batch to batch.
batch to batch
So
variability.
uh, yeah, but how is it a spatial variation? Can you explain? Temporal, I
It's
can
inter
understand.
die too. That's why
Inter die, there is no
it's
variation,
inter
right?
die too. The variability.
There is no variability. So on the same wafer, on every die, we are
Okay.
getting a faulty device at the same location. The same device is getting faulty. So how is it a spatial variation? So
Okay.
I was thinking it's only temporal variation.
Okay. Yeah.
So maybe some fault like this particular wafer didn't get coated properly,
Because
or
yeah,
the resist coating
there may
thickness
be
is
like
less,
that fault
or
too.
So that is all temporal,
Yes,
right?
from batch to batch.
Yeah, from batch.
Huh.
Okay. Yeah. Okay.
But spatial should also be there.
So say in this same die, if I had um so in
Hmm.
the same die, if I had two copies of this same device, one device here, one device here. Okay. Sorry. One device here, another one here, and I am saying that only one of them is getting faulted in all the dice. Still, you will say, yeah, then it will be spatial variation, right? Because at this place it is uh, no. Then it's not spatial variation. Uh, I don't know. Okay, this question we will leave it for now. We will check it later. In design flow, design rule check is done prior to lithography rule check, true or false.
When it, that's why I'm saying it will be special variation as well. But if you consider the same frame of reference for spatial variability, then it's not spatial variability.
Okay.
Since the batch is changing, so that's why. And in any change of batch, it should have spatial variability.
Okay, so you're saying it is both.
The practically at least. Practically at least both.
Okay. So Mir is asking if I can explain both the variations. So I'll just brief them for him. So yeah, spatial variation means so say I have a wafer, okay, and on or rather than a wafer, I'll say I have a die. So in a die, uh, mm, so okay, so in a die, I am seeing a variation in the pattern across the die. So it's like something like if my PR is not getting coated uniformly. Say I had this small chip here, and I coated spin coated it, and so the PR might have got distributed somewhat like this in a circular motion, and so the photoresist thickness here at the corners will be lower compared to the center. So that will affect my pattern underneath. So this is so say some device here might be functioning well, while some device here might not be functioning well. So this is spatial variability. So even though I am writing the entire die at once, so temporally the entire thing is written at once, but because of the spatial locations of the devices, the device at the center will work fine, the device at the edge won't work fine. So that is spatial variation. Now say this was my device, this time it worked fine, next time I take similar kind of chip, do a similar spin coating process, and the same device at the same location, now it is not working well. So this can be due to say the lithography setup that I used, uh, the exposure was not proper, or maybe while developing it I overdeveloped it. So uh, so now it is across two different wafers or two different samples. So when it is across two different samples that were temporally separated, so this I processed first, then I processed this, so maybe the humidity became out of spec by the time I processed the second wafer. So because of such reasons, then it is called temporal variation. Variation across wafer to wafer. But in the same sample or same reticle or same wafer, when I see variation due to the same device being at different spatial locations, then it is spatial variation. Is that okay, Mir? Okay, I will proceed. Okay. Uh, is everyone else able to listen to me? I think Akash is facing some issues. Uh, I hope the problem is not at my side. Thanks, Sarla. Okay, I'll proceed. Which of the following affects the thickness of material removed in CMP? Select or okay, we finished this, right? Sorry. In design flow, design rule check is done prior to lithography rule check. State true or false. Okay, so first of all, what is design rule check and what is lithography rule check? So whenever we go for lithography writing, right? We first give a design. So we first have an idea, and based on the idea, we make a layout. So this design that we give to the foundry or to the mask manufacturer first, and then so this design we should first see if it is okay to be fabricated. So every foundry will have a process design kit, and that process design kit will give some design rules that we need to check before sending our design to them. So these design rules are checked at the designer's side. So this is the DRC that we do. So say the critical dimension they will give. So if the spacing of my say metal spacing or design spacing is within the critical dimensions, so they will also give some angles. So if my interconnects are at 90-degree angles, so say I had a metal pad here, I had a metal pad here, I wanted to connect these two, so I can either connect them like this, or I can connect them like this. So there are specific rules regarding all these things. So many foundries won't allow you to uh, give such slanting lines. So you will usually give 90-degree bends. Also they won't allow you to give acute angles, because then yield will reduce at the acute angles. So all these things, all these rules are there that are provided by the either the lithography tool manager or the foundry that you are sending to. And these rules we need to so our design should adhere to these rules, and that part is called design rule check. Lithography rule check is done by the lithography engineer. So once your design is sent, it passes all the design rule checks. When it goes to the lithography step, they also need to do some layout checks. So the general process flow of how things go on is like, first you have a design, I'll write it here, then you do a DRC check. So if it passes the DRC check, then you go ahead, or else you again go and change the design. Once you have done the DRC check, uh, you usually uh, check the layout versus the schematic. So whatever schematic you had thought, is it the same, that like, so all the interconnects are the same, and you are not accidentally making some other device out of your layout. So yeah, so this is an optional step. Usually the design will be correct. um, so you will usually check all these things at the design stage itself, but after this you will also do a optical proximity correction, OPC. So in your layout, even though you might be in the critical dimension, so the DRC might be passed. So say the critical dimension was 0.5 micrometers, so this is 0.5 micrometers, but in some places everything is close by, so everything is at a distance of say 0.5 microns, but in some other places things are like one line, sparsely populated. So the proximity in such is different for this and for these. So based on the proximity, there will be the like exposure might be different, so that will give a different yield at different places. So here for the light to pass this mask, because all the designs are close to each other, the optical field that it sees at the wafer might be something like this, whereas here it will be higher. So the proximity effects might come in, so you need to simulate for all these things. So that is done at the optical proximity correction, and if even after this we need to check uh, uh, after this we need to check the lithography rule check. So these two basically go hand in hand. So because the layout might have such structures, so we do a optical proximity correction, and after the optical proximity correction, so you might put some uh, dummy fill portions in the areas which are sparsely populated, just so that the density of population remains constant overall. So whenever you are doing lithography, right, so there will be multiple reticles. Okay. So in each reticle, if there are some places of high density and some of low density, because you are exposing the entire thing with the same exposure dose, so it will create problems. So it's better to have everything of same pattern density. So to make sure that everything of everywhere the pattern density remains the same, we add some dummy structures, some cross or a series of boxes, just like that. So they won't affect the device performance, they are just there to fill the layer. So that is optical proximity correction, and after that we need to check if everything is uh, equally dense, or so all those checks are done in lithography rule check. So basically what they will do here is they have a model or a process a model that they run on a computer. So based on whatever layout that we have made now with all the dummy uh, dummy boxes also, so this layout they will feed into the model, and they will see um, what will be the mask output that we get. So in software they will check. So before actually going ahead and fabricating the mask, they will check in the software based on the model what are we getting and is it what we require. So that part is done in lithography rule check. So this is usually done by the lithography engineer or whoever is fabricating the device for you. So DRC is done by the designer, lithography rule check is done by the foundry or by the team lithography team. So then this follows the mask preparation. So that is the general flow. So after the mask is prepared, you go ahead and do the stepper or scanner or projection lithography steps. Okay. Can I move ahead? Thanks. Okay. Which of the following yield issues can be known after characterizing the device performance? Okay. So, so yield is again how many devices are working, right? So there are different types of yield and different type of yield issues. So there is lithography yield issue, pattern dependent yield issue, and parametric yield issue. So what is lithography yield issue? So say I uh, wanted a pattern like this on top of my wafer, uh, but say I am getting something like, so like the trench in between has disappeared or something like that. So we don't know if the device still works or not, but we know from just looking at the lithography step that the lithography has not come exactly as we wished. So that is termed as the lithography yield issue. Pattern dependent yield issue, again just like I said previously. So because of so somewhere the pattern might be dense, somewhere the pattern might be sparse. So based on that, so say I am having a positive resist. Okay, so the mask here is very dense and here it is very sparse. So, positive resist means whatever is exposed will get removed, right. So, say this is my silicon substrate and I am exposing the PR on top of it. The PR here will look like, after exposure, after development, it will look like this. So, you see here it is getting resolved because these are sparse, but here since they were very close, the light coming was not able to properly expose these parts, or you might even get complete exposure like this. Oh, sorry. It might happen that here everything has disappeared. So, such things can happen because of the proximity. Uh, so, this is a lithography yield issue. So, sometimes these yield issues are not that critical, so the device might work at the end of the day, but still in terms of lithography you will call it as a bad device. And sorry, this was the pattern dependent, the one with proximity unknown. And the third one is parametric yield loss. Parametric yield loss means, say I fabricated the device and now maybe there are some lithography errors, maybe there are etching errors, maybe there are pattern dependent errors. We regardless of all the errors, some of the devices might work, some of the devices might not work. So, some devices the defects are very few, so they might work. So, even though lithography yield wise that device was didn't yield, but when we check the device performance, it has yield. So, such loss I term it, they call it as parametric yield loss. So, after doing the device characterization, if your device is working just like you wanted it to work, then you say that that device has yielded. The devices that don't work, you say that those devices have not yielded, and the corresponding loss, that is how many devices didn't work, is called as the parametric yield loss. Okay. So, decreasing die size will increase yield, decrease yield, increase die to die variability, decrease die to die variability. Someone wants to take a guess? So, increasing die size. So, just as I said, so in a wafer we usually write multiple dies. Okay. So, if I increase the die size, so instead of having, so if I say I go for bigger dies, so now I have only 4 dies. So, increasing die size, will it increase my yield, decrease my yield, or increase die to die variability, or decrease die to die? So, this variability means uh, what is the device dimensions in this compared to this. So, what is the change, or so you have different parameters, right. So, say there is a wire here, the resistivity of the wire here will vary die to die. So, what is this variability? So, that is so will that variability increase or decrease? So, it is decreasing die size. Okay. So, it is going from this to this. So, first we had bigger dies, now we are having smaller dies. So, will it increase yield? Okay. So, maybe we have some defects around. Uh, say we had a few defects like one here, one here, one here, another one here. So, on this wafer there were say 4 defects. So, in this case the yield is 2. two of the dyes have yielded, other two are faulty. So now if I decrease the dye size, now how many have yielded? So one is here, one is say on this, another one is on this, another one is here. So now how many have yielded? 1, 2, 3, 4, 5, 6, 7. So the yield has increased, right? Yes, you are right, Mir. Increase yield. So this is wrong. But what about the variability? So variability, uh, so the variability will actually uh, decrease. So now, since the defect density remains the same, so it's like, say there were, okay, see there were some defects here and there. So in addition to the earlier defects, I am just making more defects to illustrate the point of variability. Um, so the orange ones are the defects. In spite of those defects, the device is still working, say, and the blue ones are terminal defects, say. Then these defects are introducing some variability, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So these defects are introducing some variability. However, so the variability here, okay. So if you look here, this die is completely free of defects. This die has two defects. This guy has one defect. This guy has one defect. This guy has no defect again. This guy has two defects. This guy has one defect. In this one, both of them have two defects. That you may say is because of my cleverly positioning the defects. But you can imagine that when we have a larger area, the number of defects in the larger areas, because of the common defect density, they will usually be similar. However, when we have smaller areas, there is a high chance that some of them might not have any defect at all, while some others might have some defects. It should decrease. No, so we are decreasing the die size, right? It will increase the die to die variability. So here some of the dies are perfect, some of the dies have more defects, some of the dies have no defect. Here both dies have similar kind of defects. So from going from higher die size to a lower die size, we have increased the die to die variability. Am I making sense? Um, okay. The variability is higher in this case simply because when we have larger areas, it is uh, the defect density remains the same. So the number of defects here and here might be similar. However, in smaller areas, the chances of getting perfect dies increases because it's a smaller area, right? And the chances of having very high accumulation of dies, so it gets kind of averaged out in this case. Okay. Which type of process are carried out at high temperatures? Front end processes or back end processes? Okay. So first of all, what are front end processes and what are back end processes? So front end processes are basically, so whenever we are fabricating a device, first we take a wafer and so just on top of the, so now the wafer is in its purest form, right? So just on top of this wafer we will have an active layer of devices. So there might be some doping, there might be some special materials. So all these are the, this is the first few microns on on the top of the wafer is called the device layer or active layer. So all the processes that are used for fabricating this device layer, all these processes are termed as the front end processes. Now once we have the device layer, this device layer usually requires, um, so there will be some metal pads on top of the device layer, and we need to connect these metal pads to make connections between different devices. So there will be different devices here, transistors, resistors, capacitors, everything, and then we need to connect these devices. For connecting these devices we have multiple interconnection layers. So there might be metal pads, metal contacts, uh, vias, everything in these layers. So all these layers are called, all these layers are called interconnect layers, and all the processing, so deposition, etching, or uh, chemical mechanical polishing, all these processes come in the back end process. So the device layer, where where everything is in the purest form, comes uh, is fabricated using front end processes, and when we start depositing metal on top of it, so all those processes become the back end processes. So which type of processes are carried out at high temperatures? So do you think the device layer, fabricating the device layer, so the front end processes will be carried out at high temperature or the back end ones? Anyone wants to give a try? Okay, so I'll tell the answer. Uh, right. So actually, high temperature, we can go at high temperatures only when we have no or very less metal. So what happens is metal ions usually diffuse very fast through the silicon. So if we desire high purity of our active layer, we don't want metal to diffuse into the active layer. So usually the interconnects, so for making the interconnects, that is when we are doing the back end processes, we cannot do them at high temperatures. So these are usually low temperature processes. So all the high temperatures processes, we need to do it at the starting of the fabrication itself. So when when our silicon is very pure, when what the when we are doing doping and everything, so doping might require high temperature, annealing might require high temperature. All those processes we are doing at the front end. Even some depositions, so some thin film depositions require high temperature. So those we will do at front end. Once we start putting metal, it becomes very difficult to do high temperature processes. Okay. Okay, a certain sample is brought for CMP, right? So this is a sample that they have given us for chemical mechanical polishing, and after CMP they expect the profile to look like this, but when we actually do the CMP, it is looking like this. So there is a curve here. To avoid this, shall we increase the density of metal? So this is the gold metal here. Should we increase? Should we put dummy gold so that the gold density increases, or should we decrease the density of gold? So first of all, what is this phenomena called? Does anyone know? Okay, Mir is saying decrease. So we have to decrease the metal density. Okay, so if we decrease the metal density, what will happen? We'll have, so this is my silicon, silicon. So now the metal is thinner than before, because metal is very far away. It's like the distance between the two metals is more compared to the metal film deposited. So now what will happen is, so now the SiO2 is at on a larger area. So now what will actually happen is, this phenomena will increase even more. So in CMP what is happening is, this SiO2, whenever we are doing this chemical mechanical polishing, it is easier for the slurry and for for the slurry to remove the SiO2. So the abrasives in the slurry will easily remove SiO2 compared to gold. Gold is very hard to remove. So what will usually happen is, it will go ahead and remove more SiO2. So to prevent that, what we can do actually is to increase the gold. So um, if I have gold even in the middle here, now what will happen? Now the SiO2 will reduce from this part, but then again there is gold here. So here it will increase again, like not increase, here it will be just, so earlier it was like this. Now if I just put one more gold here, now the trench is very small, so the slurry cannot, it's difficult for the slurry to penetrate, so it will just go a little down and come back up again. So this phenomena, this is called dishing. So this dishing will be less compared to having lower metal density. So it is actually preferable to increase the density of metal. The reason being simply that it is difficult to etch the material, so etch the metal compared to SiO2, remove the metal compared to SiO2. So because of that, if there is less SiO2 that is exposed, so it will be more difficult to remove it. So it is happening because it is easy for the slurry to reach the center compared to the sides. So if it becomes more tough to reach, then it is difficult to remove it. Okay, thanks. So now same question, but in this case what happened is, because of whatever was the slurry chemical composition and whatever was the pressure that was applied, in this case what happened is, even the gold thickness reduced. So the CMP process was not very selective for SiO2 and gold. So both of them reduced. So this was the expected thickness and this is smaller than that. So this phenomenon is actually called erosion. So whenever we are doing a CMP process, there are these two things. One is dishing and another one is erosion. So for erosion what should we do? Increase the density of gold or reduce it? It is like a very mechanical process, right. So if the sorry, not mechanical, kind of chemical process, right. So CMP, right. So it has both mechanical and chemical parts, but the chemical nature is such that now in this case that it is etching both. So whenever the selectivity is less, so even though it is preferred to etch SiO2, it is also etching the gold. So if we increase the okay, if we increase the gold density, so then what will happen? There is gold here, gold here, gold here. So then there is more gold area available to etch. So the CMP will remove more gold, but we do not want the gold to be removed. So if the density of gold is less, so 1 and 2, then it sees more SiO2. So then it is easier for it to remove SiO2 and less gold. So, so there is always a trade off. So for dishing, we said that we need to increase the metal density, but increasing the metal density will expose more amount of metal to the pressure and to the slurry chemicals and abrasives. So, so that will create the problem of erosion. So for erosion, we need to reduce the density of metal. So what is said that uh, to prevent dishing problem in layout, we should maintain a minimum density of in this case metal layer or any particular layer that is of interest, and to prevent erosion we should have a maximum density of metal layer. So we should not go above some maximum density. So if it goes above the maximum density, the slurry will start etching the metal as well. So there is a sweet spot for the pattern density that we should adhere to. Okay. Okay, so this was all about CMP and design for manufacturability. I would further move on to again the previous topics and discussing some important questions on the previous topics. Before that, if anyone has any doubt in till here, they can ask. If not, I'll just move ahead. Okay. Okay, so this is about just designing a process flow. A simple PN junction diode is shown in cross section in this figure. So this is a cross section of a PN junction. Make a possible process flowchart for fabrication of this structure, including mask steps. So this is what we need to fabricate. This is P-type silicon or any other P-type material. Then we have doped it with N-type. Then this is the SiO2. Uh, yeah, this is the passivation SiO2. So just to isolate this metal from this metal, and, this is aluminium metal basically, and then this is the contact. So so yeah, this will go to the wires or anywhere else wherever we so basically we'll just, so this is the device and this will just give the power or voltage to this device. Okay, so to fabricate this device we have to design the process flow. So the first thing would naturally be to take a p-type silicon wafer. We choose a p-type silicon wafer, desirably very pure wafer. Then what will we do what will we do next? We need to dope it, right? So for doping, we don't want to dope the entire device region, we just want to dope a particular region. So for doing that, we can do, so for doping there are multiple approaches that were taught. There was a diffusion based doping, ion implantation based doping, but we had learned that ion implantation is, in ion implantation we can control the depth of penetration very well. Also we can do ion implantation by simply using a photoresist mask. So I would say that second step we can go ahead and do a ion implantation. So this is just a choice, we can also do diffusion. For diffusion we can make a first hard mask, SiO2 mask, and then we can send the diffuse some uh, some gas or liquid composition that will diffuse through to give us such a profile, right. So but say we do a ion implantation. So second step is ion implantation, and for before end implantation we have to do a lithography step. So since they are asking us to make a note of all mask steps, let me say the second step is first we have to code the PR, right? So I'll say it is litho 1. Okay, so first we had a wafer. Now we have patterned the wafer such that the resist is here everywhere. Just wherever we wanted the n type doping, it is open. Okay, so this is PR. So what is the third step? Third step, as we discussed, is ion implantation. So this will naturally be followed by resist strip or resist removal. Okay. So after that, what did we have to do? So now we have to deposit this SiO2 layer, right? So step 5 will be SiO2 deposition. So we can probably use any of the CVD steps that we have learned. Preferably not high temperature ones, because that will change the diffusion profile of the n type dopants. So say PECVD. PECVD is also high temperature, but not as high, I guess. So some deposition step, we can even do a sputter deposition. Sputter is room temperature. But then the quality will deteriorate. So if we go for lower, even lower temperature, so we have to choose, like based on how much is the temperature budget of this device, we will have to choose between different CVD options and physical vapor deposition options. So right, step 5. Now step 6. So once SiO2 is deposited, now what we need to do? Now we want to pattern it. So open the SiO2 in certain positions, right? So this metal should touch the p type part and this metal should touch the n type part. So it should open at these two positions. So for that we have to do another litho step, litho 2. Uh, so so now my device will look like, there is n type silicon here, there is p type here, and there is SiO2 everywhere. So this is just for passivation, like for making sure that the contacts are isolated, and then I am doing a PR coat here. So this is my photoresist. So it is open at these two positions. So now once I do the etching step, so etching will remove these regions, right? So now I will have N, P, and there is SiO2 only here. So till here now we have made. Next what we need to do? Now we want to put the aluminium, right? So now for putting aluminium, so so again we don't want to put it everywhere, we want to put it at selected particular locations. So what we can do is we can do a lift off process. So again that will be a litho process first. So by doing lithography we will okay, I'll just draw. We will put PR in these locations. Right. So this can be done using the same mask that we used here. Right. It's just by here we, yeah, it's just the same pattern, right? Again we are making the same pattern on top of this. So we can in principle use the same mask, but if we want a slight width here, just to be on the safer side, we'll have to make a different mask, and so that will mean that we need a third mask, so that this metal is slightly white, that's like shown in this picture. Then we will sputter. So I'll write it. So this was by litho 3. Then step 9 is sputter aluminum. So we'll sputter coat aluminum on top of everywhere. So there will be aluminum, uh, there will be aluminum here, 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 everywhere. Right. So now what we will do is we will lift off. So by lift off, which means that we will remove this resist. So the blue portions we have to remove. So we will use some solution that will dissolve this resist, and with that the aluminum that was deposited on top of this resist will also get removed. So this process is called lift off. It will be step 10. So that is the last step. Sorry. So after lift off, my sample will look like P, then this is the SiO2, and there is metal. So that is exactly like how we wanted it to be. Okay, is that fine? Thanks. A complex CMOS fabrication process requires 25 marks. What fraction of the dies must be good, that is what yield must be obtained during each mask step if we require 30% of the final dies to be good? How about if we require 70% to be good? Right. So we have 25 mask steps. So 25 times we have to do the lithography, and each mask step will have some yield, right? Some of the dies might yield, some of the dies might not yield. But finally, once the entire device is made, we require that at least 30% of the final dies to yield. How do we do that? So if we want so the probability of final die to yield should be zero point 0.3. So that is nothing but probability that it yields in first go into probability that it yields in second go, and so on up to probability that it yields in the 25th go also. Correct. So say that all these probabilities so all the mass steps are equiprobable, so then this is nothing but p to the power 25. If all p1, p2, p3 are all same as p, then p power 25 should be 0 0.3. So if you just calculate this will give you p to be just do it. It will give you p to be something around 95.3. Sorry, not 95.3, 0.953. You can just cross check it. So that means that we need to have a 95.3% yield. Uh, yeah. So what fraction of the dies must be good? So 95.3% of the die must be good during each mask step if we require 30%. So similarly, can you do for even 70%? Same thing, like we just go on and say p power 25 equal to 0 0.7, and we find out p. So that will be somewhere around, if you do it, it will come out to be somewhere around 0.986. So that means 98%. So you see, right? So if we want a higher yield, we have to be almost perfect in each of the mask steps. It should be almost 100% yield every time. So even if it's almost 100% yield every time, we will still get only 70% good dice, because the number of mask steps are so many. Okay. Why chemically amplified photoresist is used starting from deep UV to 193 nanometer illumination systems. So these are basically low wavelength illumination systems. So they are asking why these low wavelength systems need chemically amplified photoresists. So first of all, why we go for these smaller wavelengths? So lower wavelengths means better resolution, right? So we have studied that resolution is directly proportional to lambda over numerical aperture. So as we go on reducing the lambda, the resolution will go on reducing, that is smaller resolution is usually the better resolution. So to improve resolutions we go on reducing lambda. So that is why we use such very exotic sources. However, the problem with these sources is that these deep UV sources or even soft X-rays like 13 nanometer sources, they they are very relatively weak sources. So the intensity of light that will come out of these sources, or the number of photons that come out of these sources, will be very low. So it's like, okay. So since they are so weak, that means that we have to improve the quality of the photoresist and make it very efficient. That's why they use chemically amplified photoresist. So chemically amplified photoresists are usually more efficient. Right. And why are they able to be more efficient? So it's very simple logic. So see, in standard resist technology, if you give one photon will alter the solubility of a group of molecules, like uh, a very small group of molecules alters, and that's it. Like it will not do anything else. Whatever is exposed, it will alter their solubility. But when we so this is for standard resist. Okay. So when we use chemically amplified resist, what it will do is single photon from the source. So these are very weak sources, right? So every photon is very costly. So a single photon will start a chain of reactions. So not just a single, it will trigger multiple chain of reactions. So because of this, uh, large group of molecules, like many molecules will get exposed in the single photon. So uh, a photon might give energy only to a single group of molecules, but then this single group of molecules will catalyze some reactions and uh, make even the neighboring molecules soluble. So for for making the same area uh, of photoresist soluble, uh, we require less intensity of incoming light. So fewer photons are needed for exposing similar areas. So because of that, chemically amplified resists usually are more efficient compared to the standard resists, and they are better for such exotic sources like deep UV 190 nanometers or even 13 nanometer X-ray, like soft X-ray sources. So these sources are relatively new and their power is very low. Because of that, we need such special photoresist. Okay, another descriptive question. So I just included these because like this month you guys might have exams, so it might be important, like even to be um, even if you get descriptive questions, so it might be helpful. So briefly explain how resolution enhancement is achieved by uh, the following three techniques. So, first is high contrast photoresist. So, yeah, so how can we achieve better resolution or resolution enhancement by using high contrast photoresist? So, first of all, high contrast photoresist will definitely yield better resolution because because the energy range over which, so what is high contrast? First of all, high contrast is basically, it means that if this is my intensity, optical intensity, that is of the incoming photons, and this is the PR thickness after development, then for the regions where the intensity exceeds some threshold intensity, the PR thickness will go up, or depending on whether it's positive or negative. But this region, right, the region where it's going from a low PR thickness to high PR thickness is very small, or else in other words this slope is very steep. So that is high contrast photoresist. If it was not that high contrast, so low contrast photoresist, it might have gone something like this. So there is a gradient in thickness. So but in case of high contrast, we have a very sharp change. Because of that we get very sharp images. So this is very good when we want to have uh, very closely spaced structures, or when we want better resolution. So when we want to go for smaller critical dimensions. Uh, Nabajit, yeah, sure, I'll share the slides. Okay, so yeah, so whenever we get a dose, so whenever we are exposing, right, so the dose profile at the surface which gets exposed. So say I have a mask like this, it opens in these two positions. So when I plot the optical intensity versus the position, say this is the x axis, so this is also x axis, and this is the intensity. So this is the intensity of light that comes to the wafer. So ideally what I want is, ideally I will obviously want a profile like this. So whatever is open should get exposed, whatever is not open, the intensity should be 0, so it won't get exposed. But in real life what we get is different, if is something like this. So this is due to the diffraction, right? We know about this. So because of this intensity profile, when so when we expose the photoresist and we do the development, we'll see we'll see non-idealities. So ideally we wanted the resist to look something like, say this was a positive resist, then whatever is exposed will get removed. So the resist will look something like this, this and like this. Okay, so we wanted it to look like this, so this is ideal, but real will look like, because it's taking some time to ramp up, right, and it's taking some time to ramp down also. Sorry. So there will be this gradient, because in real profile if you see, the profile itself is having a gradient, it's not as ideal as we expected. So this is the optical profile and this is what we see on the resist. So this is a typical resist, but what if we have a high contrast photoresist? So what happens in a high contrast photoresist is, if my intensity exceeds some, so here it was I1, right, if say my I1 is somewhere at this location, I1. So whenever it's going above this, sorry, whenever it's going above this I1, it will get exposed. Whenever it's below, it won't get exposed. So then my real profile for high contrast resist will look like, so this is the substrate, and on top of that, uh, so here it is below I1, so it won't be exposed. If it's not exposed, that means the resist stays there. Now it crossed above I1, so it will get exposed, and it will be like this. A slight slope will be there, might be there, but otherwise it will be there because this is not perfectly straight. It will have a slight slope, but it is way, the slope is way steeper compared to this, so it will be like this. Here again it has gone below I1, so it will again not be exposed. What happened? Again here. So if you see, the open area is much closer to the ideal situation compared to here. Here because some resist is left here, again the open area is reducing. So that is why high contrast resist is much better for enhancing resolution. So why we say it is enhancing resolution? So in cases where these two openings were very close to each other, then what will happen is my optical intensity profile would look something like going up, and then because these two will add up on each other, so it will go like this, something like this. Okay. So now if my I1 is somewhere here, so because my I1 is here, so some portion will still be not exposed in case of high contrast resist. If it was low contrast, so if it was low contrast, it would the resist profile would look something like this, but in case of high contrast it will look like this. So that is the difference it creates by having a better contrast. So that was about high contrast photoresist. Second is phase shift mask. So phase shift mask, uh, so it's a simple concept. So in phase shift mask, what we do is, so in litho we have a mask, right? We have a mask with certain openings, just like we discussed before. So there is a mask with some openings, and then there is our substrate which is coated with photoresist. This is my PR. So now this PR is getting exposed by the incoming light beams. So here it won't get exposed, here it will get exposed. Right. So now this light is coherent. So uh, in general, the phase of light that is coming from this trench is same as the phase of light that is coming from this trench, because what? It is a simple quartz mask. So glass here and then chrome here, right? So chrome won't let the light pass, it will pass directly through the places where chrome is etched, and so the phase of light that is coming from this trench is same as phase of light that is coming from this trench. So if I plot the electric field, uh, uh, so say this is x direction, across x direction, then the electric field will say if it is high here, it will also be high here. Okay. So now if these two trenches are very close, what will happen is, it might happen that, just like I said before, that the intensity coming of light coming from both the openings will merge, and because of this we will see something like this. So this is my electric field, and similarly intensity will also look like same square of electric field. So it is not going completely to 0 here. So that is my intensity. But if I now use a phase shift mask, so phase shift masks, what we do is, so again we have a glass and there is a chrome here, there is chrome here also, there is chrome here also. But now I will etch this glass a little. So now the refractive index of glass is here and it's air here. So the refractive index has changed. Now this change in refractive index, or this etch depth, is chosen such that there is a 180-degree phase shift between the light that is coming from here and the light coming from here. So there is some light coming from here and there is some light coming from here, right? There is a 180-degree phase shift between the two. So now the electric field profile across x direction will look something like, uh, if this is my 0, it will go up, and then this is 180 degree, right? So it will go down. Because of the phase shift, what will happen is, so here it is peaking here it is peaking uh, at minus e, and in the middle there will be destructive interference, because here what happened, one was peaking here, another was also peaking here, so they both added up, they both were positive, so added up. Here one is positive, one is negative, so they will cancel each other and go to 0. So when I plot intensity now, so when I plot intensity, it will look something like this. So since it is going to 0 here, the intensity will also drop down to 0 here. So that will help us achieve a better contrast. So that is the method of phase change mask, phase shift mask. Phase shift. Okay. So this is useful when we have periodic patterns. Uh, One of the disadvantages is that it's not very useful when we don't have periodic patterns. So say if I had this periodic set of lines, we can use it. But if I have something like a line and a very curved line going very close to it, so this is very close, so it is difficult to resolve, but it's like the distance between these two will keep on changing, so I cannot really put uh, so either I have to be very smart and be able to engineer the phase shift at each of these points to make sure that it always destructively interferes in the center, but in general that is very difficult. For such cases it is not possible to have a phase shift mask. So it is good for periodic patterns, but when we have isolated patterns in which two lines come very close, or two design patterns are very close, then in those cases this approach cannot be used effectively. So here we can use like one is 180 degree 0, 180 degree 0, 180 degree, but in such cases it is not possible. It is useful only for periodic structures, that is its disadvantage. And one more disadvantage is obviously the mass process becomes costly. Okay. Oh, one more was there, right? So another one is increasing NA. So okay, let me take another slide. So we had discussed this before. Resolution is directly proportional to lambda over NA, k times lambda over NA. Okay. So what will happen if we increase NA? If we increase NA, R will go down. Lower the resolution, better it is, right? So good resolution means smaller resolution. So how this happens is, the theory behind it is that when we increase Na, we are essentially capturing more diffraction orders. Uh, so if we are capturing more diffraction orders, it will make the image more sharper. So you can simply imagine that if I want to if the ideal profile that I want is this, if I just capture the first diffraction order, it might look something like this, right? So if I add multiple more orders, it will go on becoming straight. So just simply, if you have remember from your Fourier component uh, class, just by including more number of Fourier components, we are able to uh, get the waveform in the perfect shape that we want. So the similar logic applies here. If we capture more diffraction orders, then the net image that we form on the surface of the wafer will be more close to the desired image, to the image in the layout. So that will make the images more sharper. Also that will make sure that we are capturing more light. So if we are capturing more light, that will mean that we will get brighter images. Brighter images means it is easier to expose the wafer. We so the photoresist will get exposed easily. Then what is the disadvantage of this? Disadvantage, we had discussed this during when we discussed optical litho. Disadvantage is the depth of focus. So this depth of focus is inversely proportional to the square of uh, numerical aperture. So what will happen is, if we have say if I have a stack, and then the topmost layer is my photoresist. Okay. Now this photoresist thickness need not be very uniform. So some places it is thinner, some places it is thicker. This deposition variation is coming because of the underlying layers or whatever reasons. Then what happens is, some places it will get exposed better compared to some other places. So will it yield will depend on the depth of focus of the projection instrument. So higher the depth of focus will mean that this small slight variations we can be ignored. But if we are reducing the depth of focus, then we cannot ignore these slight variations, and the portions where the resist is getting thinner or thicker won't get exposed properly. So that is the disadvantage. So we can say it is reducing the depth of focus. Okay, so that was about the three. Yeah, next is a multiple choice problem. RCA cleaning is used to remove what type of contamination? Trace organic, particulates, trace metals, all the above. Someone wants to answer? Okay, in the interest of time, I'll just tell the answer. Uh, RCA cleaning is used to remove, it basically, so there are two steps in RCA, right? RCA 1 and RCA 2. So RCA 1 will remove organics, and RCA 2 will remove metal. So both. So particulates can be either organic or metal, so both. So all of the above. For application where bulk purity of silicon is paramount, which silicon wafer will you source? So basically they are asking which is the purest silicon. So definitely not the test grade or the mechanical grade. So these are sub quality compared to prime. So prime grade is the best grade, and prime grade also has two variations here, CZ silicon or FZ silicon. So Czochralski's or float zone. So these are two different techniques of purifying silicon, right? And we know that CZ silicon uses just single step process. So in single step, based on the solid solubility of impurities and silicon, we in silicon we will separate out the impurities. But in FZ we are doing this step again and again, again and again. So it is a multi-step process, and we can increase the purity of silicon as high as we want. So prime grade FZ can be made more pure compared to CZ. So if purity is of very much important to us, then we will use FZ silicon. All other things remaining equal, yield will fall if, yeah, so when does yield fall? So we already discussed this once, but this question is a bit more trickier. So if the die size is increasing, so we are increasing the die size by 10x, and but we are decreasing the defect density. So the number of defects on the wafer have reduced, but the die size has increased. So we need to look at these numbers now. Second is die size is decreasing 10 times, defect density is increasing twice. Third is probability of failure reduces 5 times, defect density increases 5 times, and probability of failure reduces 5 times, die size increases 5 times. So which of the following? So in all these cases we see that the two effects are contradicting to each other. So by increasing die size we will reduce the yield, but by decreasing defect density we will increase the yield. Similarly here, if die size is decreasing, then yield is better, but again now the defect density is increasing, so yield might fall again. Here also probability of failure is reducing, but again the defect density is increasing. Again probability of failure is reducing, but die size is increasing. If die size increases, probability of failure again increases, right? So, uh, so let us look from down to up. So probability of failure reduces 5 times if die size increases 5 times. If die size is increasing 5 times, probability of failure is again increasing 5 times. So the effect net effect is 0. Probability of failure reduces 5 times, defect density increases 5 times. So what does that mean? So even though there is a defect, the probability of failure is less, is what this means. Yeah. So see, this is my wafer. I have 4 different dies. So defect, first the defects were, say, like this. Now my defect density has increased 5 times, so there will be much more defects. However, uh, just because there is a defect doesn't mean the device will fail. So that is given by the probability of failure. So that is reducing 5 times. So I think in this case also the net should be 0. Die size is decreasing 10 times and defect density is increasing twice. Okay. So say first the entire wafer we had only one die. Now if die size is decreasing 10 times, how many dies can I have? We can have many dies. Let's not focus much on the numbers now. Uh, so say this was x, this will be 1/10 of x by 10. Die size is reduced. Say by die size if we mean length of the die has reduced 10 times. So and defect density is increasing twice. Say it had some 5 defects, 3, 4, 5. It let us say 3 defects. Okay. So now there will be these 3 defects here in those. Yeah. So now die size has decreased 10 times, defect density increased twice. However, the yield has increased lot more times. Uh, we have to say in which the yield will fall, not increase. So in this case the yield has increased, right? So here the yield was 0, say each of these defects are terminal, then it is 0, but here it is 1, 2, 3, 4, 5, multiple. So yield increases in this case. So this is the opposite of this scenario. First scenario, die size is increasing 10 times. So say this was my, this is case 2, this will be case 1. So this is the original and this is the new one. So die size is increased 10 times, defect density is reduced twice. So here there are 6 defects, here there are only 3 defects. However, uh, this one won't yield because there is just one, and even if there are 1 or 2 terminal defects here, it's gone. However, here there are many more dies available. So uh, so now what do you think, Mir? It should be 1, right? Because that will make sure that the yield falls. The 2 will make sure that the yield increases. Is that okay? Yeah, thanks. For growing thick native oxide of silicon, which would you prefer? So this is just technical question. Like when we want to grow thick oxides, we usually prefer uh, higher growth rates, and higher growth rates among these options are achieved in wet oxidation. So wet oxidation is the correct answer. You can go ahead and look at the H rates, sorry, not H rates, growth rates of native oxide in all these cases. So, you will see that wet oxidation is the best option. What can be a side effect of soaking silicon wafer in HF for a long time? Yeah, so if you put silicon in HF solution, what will happen is, although H rate of silicon is very slow in silicon in HF compared to SiO2 SA, but HF will still etch some of silicon, and that etch rate will depend on the crystal orientation. So, whether the orientation is 111 or it is 100, that will that will decide if HF is going to like the H rate of HF. It's very slow, but it's still there, and it's maximum for the case of 100. So, or rather minimum for the case of 111. So, uh, I don't really remember the numbers which orientation is maximum and minimum. However, the the point I am trying to make is, it will depend on the orientation. So, some of the orientations will be preferentially etched, others will not be etched. So, that will increase the roughness on the surface. So on the surface, some say it is etching in this this orientation, but it is not etching the diagonal orientation. So, then those will remain. So, it will become rough. So, that is called micro roughness, and it will increase the micro roughness on the surface. Etching of silicon, that will take very long time. HF does not etch silicon at it should be etched. Uh, that is also not true, it does etch it, but very slowly, and that will just create some roughness on the surface. Smoothing of the surface, no, because just as I said, it is orientation dependent, and that will make the surface even more rough. Some of the orientations only will get etched. In order to increase diameter of silicon ingot in the CZ process, we should, so I think this is the last question. No, one more. So, if you remember CZ process, we usually had the silicon ingot that we were pulling from the solution. So, the solution will have more impurities compared to the ingot. So, it is like a crystallization process, simple uh, crystallization, like just like we do sugar crystallization in a sugar syrup, this we are doing silicon crystallization in silicon melt. So, if we increase the pull rate, what will happen? If we increase the pull rate, there is less time for the crystallization to happen at this place. So, if there is less time, the diameter of the ingot will be smaller. If we decrease the pull rate, obviously diameter will be bigger. If we increase the heating rate of the melt, if the melt is hotter, it will take more time to crystallize. More time to crystallize means at the same pulling rate, the diameter of the ingot will be smaller, and decrease the heat loss from the melt. Is the heat loss from the melt is same as increasing the heating rate, I guess. So, it will have a similar effect. So, from all the possible options, decreasing the pull rate is definitely the best option. So, if we decrease the pull rate, there is more time for crystallization to happen, and the ingot will be having a bigger diameter. Will increase the diameter. Last question, sorry. Heterogeneous nucleation refers to, okay, nucleation on non-native surfaces. Example, nucleation of silicon on the furnace tube but not silicon wafer. Okay. So, okay. So, right. So, there are two possible places for uh, uh, nuclei to form. One is in the gas phase, one is on the wafer, and one is in the furnace, right? So, nucleation on non-native surfaces. Example, nucleation of silicon on on furnace tube, but not on silicon wafer. So, uh, so is this heterogeneous nucleation, or nucleation in the gas phase is heterogeneous, or nucleation in the presence of catalysis is that, or nucleation of adsorbing atoms on any surface like wafer, furnace, etc. So, there are two types of nucleation. One is homogeneous Other one is heterogeneous. So homogeneous is when it forms nuclei in the gas phase, and then these nuclei will adsorb to the wafer substrate. And heterogeneous means it will form nuclei on some surface. Now this surface can be even the chamber wall or the substrate, wafer, anything, or even the pipes. So whenever it forms on the wafer, then such nuclei are called heterogeneous nuclei. So fourth is the correct answer. Okay. That's it for today. In the next class also we will first do the problems for the next week. Next week is I think the last class, and then I'll discuss some other important problems for for your exams. Yeah. Okay. Some reason it's not letting me stop share. Okay. Uh, so that's it for today. Thank you so much for attending. If you have any questions, you can email me, like even the previous assignment problems or anything. I'll prepare them for the next class. Thank you. I'll just. How can we get previous year papers? Uh, so I did not do any NPTEL course till now. Uh, I'll share you my email address. So I have done a course here at IISc. I can just send you the questions that we had got. So I have midterm questions and assignment questions. Final exam I don't have actually. I can share you the questions if you just write to me in the email. I'll send my email address. It's there in the chat box. Can you see it? Yeah. Just write to me. I'll mail you whatever material I have. I think that should be enough. If not, if you have any problems that you want me to discuss, I can do them in the next class. You can reply back to me. Thank you. Thanks Nabajit. Thanks Mir. Okay, so I'll end today's class.